Welcome back. Let's start. In the last lecture, we were talking about the nesting forces. So, we will continue from there. So, just try to recap. So, what we are saying here that if we put a fourth post, that may not be enough to provide nesting force. So, the fourth post is always over constrained and it does not replace the nesting force. And why? Because again it's still rigid if we consider this case. So, in order to provide sufficient nesting force, it should press and there should be, so these are the contact points. So, there should be always some force acting on the post, and that will only happen if it applies some force here. But since it's also a rigid post and the dimension of the object is also defined, so it's very difficult to get accurate dimensions there. So, either it will be too tight, so it will press too much, so there will be interference, or if there is any gap, so there will be no contact. So, no contact means there is no nesting force. So, it is very important to understand that we cannot use the same kind of contacts to get the nesting force. Another thing to also note down is the way we define the nesting force, what we are saying is along the contact point. So, it is always coupled with the contact. So, we can always say there is a nesting force, right. This is the nesting force at this contact along C2 we have this is the nesting force, what we can say, and C3. But we can always get a single force by combining them vectorially. So, that is something we also need to understand, and we will do some exercises on this, how to find the nesting force. So, there are different ways, and without creating problem, what we discussed in the earlier slide, how to get the nesting force. So, one is the weight. So, because of the weight, we can always get contacts, sufficient contact. So, weight can also provide sufficient nesting force, but many times we do not have that luxury. Other is the eccentric cam. So, you can see, and if you rotate, yeah, so this is the center, but it's pivoted here. So, as we turn, we get the wedging effect and we can lock it, and again we can get the sufficient nesting force here. Similarly, if we have a spring, so we can use compliant members. So, any kind of springs we can use, and we can press it and we can get the nesting force, and again we can get all the contacts made. So, it is very important to understand that at the contacts we should always have a positive force acting there. Negative means, yeah, there is no contact. So, there is no question of, or there is no question of getting negative values, yeah, it will be 0 or positive. 0 means we have to find some ways to get the sufficient contact. Another is the screw, we turn and then we can get the force here, and then we can get the contacts. So these are some of the methods. Magnets are also one of them. We can use magnets as well, or vacuum. There are many ways. So as needed, I think that can be done, and we can achieve sufficient nesting force. And it's a very important to have that nesting force, then only we can define the exact constraint design, or can ensure that we get the desired degree of freedom and constraints. There is a way to calculate the nesting force. What we also need to find is nesting force window. So there is a window, and if any force passing through that area, so in this case is the unshaded area. So if any force passing through that area, that's a yes. So it's a feasible solution. And if it's a passing through the shaded region here, what we realize that it's a no. It's not going to give the sufficient nesting force. So not all the contacts will be made, and it will get lifted. So maybe we'll quickly try to see how to find it, how to find the nesting force window in this case. So for instance, we have this post 1, so contact. So define the contact C1, post 2, and we have the contact C2, and then post 3, contact C3. So what we can now define is the constraint lines, which is defined along this. So this is what mentioned, nesting force direction constraint because of the 1. Along C2, this is because of the contact C2. So these are the constraint direction. Similarly, if we pass through point C3, so this is because of the contact C3. So these are the constraint directions. What we also understand that if we take 2 of these contacts, they always create a instantaneous center of rotation. So we can find ICs. So for instance, if we take C1 and C2, they are intersecting at this point. So call it IC 1, 2. So if we are considering contact 1 and 2 only, the object can rotate along IC 1, 2. So if we want to have contact with post 3 or want to make contact C3, the nature of moment, any force if we are applying, any nesting force we are giving, the moment at IC 1, 2 should be such that it will try to make positive contact with post 3. So how is possible? So one of the ways, so if you apply this clockwise moment at IC 1, 2, what we realize that it presses against contact C3. So this is what is desired. Similarly, if we take C2 and C3 together, the intersection point will be here, and which we can label it is IC2, 3. So if we try to rotate the object along IC2, 3 and only considering contact C2 and C3, but we realize that it can rotate. But if you want to make contact with C1, so it should push against post 1. So, it means the nature of the moment acting at IC23 should be in this direction, which is again clockwise at IC23. Similarly, if we consider C1 and C3, so the intersection point is here. So, C1 again, so C1 direction is this and C3's direction is this. So, the intersection point will be here and we can call it IC 13 or 31 is the same. So, call it IC 13. So, if we consider only post 1 and 3, the object can rotate along the axis IC 13. So, in order to make contact with C2, what will be the moment required? So, in this case, the rotation, the moment required will be along this direction, which is now counterclockwise. So, any force acting or any external force, nesting force we want to use, we have to understand that all these three conditions should be met together. Then only we should be able to get the sufficient contact or contact with all the three contacts, three poles. And slowly if we start going from these points, what we realize that, so that is why if we go along this line, what you realize is a no, any force coming in this one, it will not comply with IC13 requirement, same with this one. So, this is again, so it is a shaded region, the force should not pass through this area. Similarly, if we start from here IC23 and along these lines, what we realize that if the force passes through, suppose force comes and passes through this line like this. So, because of this line along this way, what is happening is contradicting with IC23 requirement, because it is creating moment which is opposite to what is required. Same with the IC12 also, is a creating moment in the opposite direction, although it is fulfilling the requirement for IC13. So, similarly, if we go, we find that this zone, this shaded area is again not valid. So, you can check whether you have this force or coming like this force, these are all not valid solution. But there is one area which is unshaded, and if the force is passing through that one, so for instance, the one is shown here, if the force is like this, what you realize that this force is a good solution. It complies with all the three requirements. So, it gives you all the three moments at the same time. So, it is a valid solution. So, in any force, even this force is also fine. This force is also fine. So, as long as it does not pass through the shaded area, it is a valid solution. So, there are many solutions, and which one to choose, right. So, okay, it gives us a lot of options, but which one is good? So, it depends on what kind of forces we want at the contacts. We may want to have equal forces at all the contacts, or if we say asymmetric and the dynamic forces are such that the sum of the contacts should take more load. So it depending on our requirement, we can formulate, we can have some optimization also, and we can play with that and we can find the optimum solutions. But we know that as long as the force passes through the unshaded region, it will give us the right solution. So, there is a nesting force window outside which any nesting force will tumble the component and out of the stable nesting position. So, we will not have a stable nested position if the force is passing through the shaded area. So, we can again take up some examples later and try to understand.